Hello everyone, I am Dr. Arunima Verma from Department of Electrical Engineering, Institute of Engineering and Technology, Lucknow, and I am going to deliver my series of lecture, that is lecture 2 in power electronics subject with the same topic, continuing with the same topic, that is 3-phase inverter. Now, already in the previous lecture, lecture 1, I already explained the different modes of operation of voltage source inverter, that is 180-degree mode and 120-degree mode of operation, and with their points of similarity, that is 120-degree mode has got certain differences with 180-degree mode, and it has got certain points of similarity with 180-degree mode. To continue with the same, I am going to analyze the line voltage of 180-degree mode, because whatever output that we are getting at the inverter side is not pure sinusoidal. It has got certain harmonics, and it is the waveforms that are available at the output is basically a quasi square wave. That means it is not a pure sinusoid, it has got certain ripples, it has got certain harmonics which are present along with the fundamental, and which are to be analyzed, because fundamental components are to be extracted from the harmonics, and then again we can do further analysis of these modes of operation. Now, to start with the Fourier analysis of line voltage of 180-degree mode, as already told you in previous lecture, from the waveform I have taken this only this part, so as to explain how the analysis is carried out. Basically, you can see this is the waveform which was available for the line voltage, that is V R Y, in case of 180-degree mode. Now, in this case, this fundamental is passing from 0 crossover point. 0 crossover point means from this point to this point, as you can see. This is the 0 crossover point of the fundamental. Again, it is passing through midway of this point. Now, these are the points from where the crossover points, the fundamental is passing through, with O as reference, that is omega t. This is the origin which I am taking as a reference for this waveform. Now, since this waveform, this fundamental is passing beyond origin, that is minus pi by 6. So, what we do is we shift the reference from origin to O dash, that is omega t is equal to minus pi by 6 is my new reference. Is it clear? Now, in this case, we all know the generalized form of Fourier series, that is very every electrical engineer knows this one. What is a general form of Fourier series? Comprising of the coefficients, the constant coefficient O0, A0, An which cosine part, and Bn with sinusoidal part. Now, this function has odd plus rotational symmetry. Which function I am talking about? The line voltage. Basically, if we talk about this one, the function that we are talking about is line voltage of 180-degree mode. This is the function which we are considering at this instant, that is f of theta. Here is line voltage of this one, and this particular function, that is line voltage of 180-degree mode, has got odd plus rotational symmetry. Now, to make it a very specific point which I want to make to the students of electrical engineering, or particularly those who are studying with the power electronics subject, when we analyze the waveforms of different, maybe rectifier, or maybe inverter, or maybe some other device, then we see that these waveforms normally follow this pattern. They have odd plus rotational symmetry invariably present in the waveforms. Now, in this case, so we consider that if these symmetries are present, then these coefficients are automatically wiped off. That means, what I want to say is A0, An are 0, because odd symmetry is there, and rotational, because of rotational symmetry, the Bn part for n is equal to even harmonics, that is even number of harmonics are present, then Bn will be 0. So, in short, what you have to do is you have to calculate Bn only for odd harmonics, that is it. So, it becomes very simple to analyze Fourier transformation, using Fourier transformation about the line voltage of the 180-degree mode of operation. Basically, when we calculate the Bn, it is given by formula 4 by pi 0 to pi by 2 f of theta. F of theta here is VL1, that is line voltage, sin n theta d theta. So, in this case, if we say this one, Bn we have calculated as 4 by pi 0 to pi by 2 VL of theta sin n theta d theta, right. Now, this limit 0 to pi by 2 is broken in two parts, or you can say is in two parts, that is 0 to pi by 6 I suppose, and pi by 6 to pi by 2. Let us see in the waveform. I think this one is the this one is there. As you can see, with O dash as reference, 0 to pi by 6 E is having the voltage is having different magnitude, and pi by 6 to pi by 2 the line voltage is having different magnitude. So, obviously to analyze or to find out Bn, to calculate Bn, we have to break this limit 0 to pi by 2 into two parts, as already told, 0 to pi by 6 and pi by 6 to pi by 2. Now, 0 to pi by 6 VL of theta is 0, and pi by 6 to pi by 2 VL of theta is having a value which is E. See, is it clear? So, to continue with that, putting the limits and calculating Bn, you get the value as like this, 4 E by n pi cos n pi by 6. Here n is the number which will be varying from 1, 3, 5, 7, 9 and so on. That means only odd harmonics Bn is to be calculated only for odd harmonics. Now, what we have to keep in mind is these n have 3, 6, 9, 3, 9 and so on. That means it has got multiples of 3, and multiples of 3 means it has got triplet harmonics which are to be removed as well. Replace theta with omega t. Why we are replacing theta with omega t? Because in this case the waveform that we are considering or we are drawing is in reference to omega t, not with reference to theta. It is basically theta only, it is just the way of showing it. So, what we will do is we will replace theta with omega t. Now, we calculated Bn. When we calculated Bn, we will put the same value here, okay, in this Fourier series. In this Fourier series, we are going to put the value Bn and finally calculate VL 1 theta or VL theta, you can say. So, from this, if we put VL of theta as summation A0 is 0 and An is also 0, so nothing is left. So, obviously, we have just Bn to be calculated, and we have already calculated, which is coming out to be this one. Now, we are going to substitute this value of Bn, which is sin n theta. So, replace this theta with omega t, we get this as VL omega t is equal to, this n is varying with respect to odd, and we have Bn, we will put this 4 E by pi, which is a constant magnitude. So, obviously, we will take that out and bring 1 by n under the banner ambit of this summation, that is n is equal to odd and sin n theta cos n pi by 6. Again, instead of theta, we will put this here as omega t, right. Now, this is how you get VL omega t. Now, this omega t is basically with reference O dash. Is it clear? This is reference O dash. Now, to replace omega t with omega t plus pi by 6. Why we are going to replace omega t with omega t plus pi by 6? Because in this case the reference will be taken as origin. O, right. Now, when we take origin as reference, so during this period which was shifted by pi by 6, we will get back to origin and we will put omega t plus. So, all the analysis that we did with O dash, that is taking as a reference, because from the point O dash the fundamental was getting started, it started from 0 value. So, we took O dash as a reference, but actual analysis is for reference origin O. So, what we do is we will go back to the origin and put replace omega t with omega t plus pi by 6, and we will calculate the final value of line voltage which is available is this one. The same series is getting expanded in the form as shown in the figure. So, here you can see that when you put the values of n in the form of odd numbers, we get this as the fundamental. This is we get this as the fundamental component, and rest of these are basically harmonics. And the biggest drawback of power electronics devices are this only, that they introduce harmonics into the system, and we cannot forego this also, because we have to, in certain operations or in certain applications, these harmonics are really dangerous and they distort the waveform like anything, because we do not get sinusoidal waveform as such. We have a distorted waveform as quasi square wave or square wave or something of that sort, but we do not have. So, what we do is we try to we put some technology, we put some modification, we apply certain techniques from outside, and we try to eliminate harmonics in certain sense to get back to the fundamental component. Now, from this fundamental component which you have already achieved from the Fourier analysis of line voltage 180° mode, you have certain parameters which will be obtained, which I am going to show you, that is line voltage peak, line voltage RMS, then phase voltage peak and phase voltage RMS, which is already tabulated further in the slides to come. The same in case of Fourier analysis of phase voltage, because the line voltage, the nature of line voltage of 180° mode and the nature of phase voltage of 120° mode are almost similar, as we have already seen in previous cases of lecture 1, where I already told you how the waveforms are obtained and how they are similar and how they are dissimilar, both the modes of operation. So, obviously, if you have analyzed line voltage of 180° mode in the similar manner, in the same fashion, the phase voltage of 120° mode will also be analyzed. Now, the pattern is the same. You have to use that generalized waveform, that is your Fourier series, you have to use that one, and again odd plus rotational symmetry is there, as you have already calculated. You can see over here for phase voltage of 120° mode also the same pattern will be followed to find out the phase voltage, and instead of line voltage, here it will be phase voltage. The series are the same, and since it has got odd plus rotational symmetry, so obviously you have to just calculate Bn only for odd harmonics. So, after calculating Bn for odd harmonics, what you have to keep in mind is, in 120° mode of operation, the phase voltage magnitude is E by 2, calculated by applying KVL in the circuit diagram. So, we got this as E by 2, right. Replace everywhere, whatever calculations you have done for 180° mode, you just have to replace the magnitude of E with E by 2, and you will get all the calculations related to phase voltage of 120° mode. So, we got Bn, as I already calculated, Bn for 180° mode was 4 E by n pi cos n pi by 6, right. This was for 180° mode, and what we are going to do for 180°, 120°, we will replace E by 2 and we will get Bn directly, 4 E by 2 n pi cos n pi by 6. Now, the phase voltage thus obtained in this case is, again once you have calculated Bn, which you have got from this, you are going to put this Bn put Bn in Fourier series. Okay. Now, Bn in Fourier series, if you put, you will get Vph of theta, because here we are calculating phase voltage, not the line voltage. So, obviously, for the phase voltage, we will give the symbol as Vph, and we will have 4 E by pi, which is a constant magnitude, as you can see over here, and put the fraction 1 by n along with cos n pi by 6 into sin n theta, and this n is varying from odd numbers, for odd numbers. Okay. Now, you have this, you expanded this. What you have to do is, again omega t, the reference is the same, everything is same, you will replace theta with omega t, and finally omega t with omega t plus pi by 6. So, omega t plus pi by 6 is basically here, omega t plus pi by 6, you have got this, with reference क्या हो जाएगा यहाँ पे, origin, with reference O as origin, whereas in this case omega t with theta is equal to omega t, the reference was O dash. Only this much you have to keep in mind. Now, you get phase voltage for the 120 degree mode. See the difference. In line voltage of 180 degree mode, you had 4 E by pi, rest everything was the same. In this case, it will be 4 E by 2, that is it. Only difference that you have to keep in mind for the analysis, Fourier analysis of 180 degree and 120 degree mode is this magnitude, rest everything same. So, this again is the fundamental component which you have extracted, otherwise it is mixed with the harmonics which are present this. These are the harmonics present. Only odd harmonics will be present, even are already wiped off because of the rotational symmetry. Is it clear? So, in this case what we do is we have calculated Vph of omega t, sorry, as 4, instead of 4 it will be 2 E by pi cos pi by 6 sin omega t plus pi by 6 plus 1/3 of cos 3 pi by 6 sin 3 omega t plus pi by 6 plus 1/5 of cos 5 pi by 6 sin 5 omega t plus pi by 6 and so on. Okay. Now, Vph peak, if you want to have, that is the fundamental component. First extract the fundamental component, which is 2 E by pi cos pi by 6 sin omega t plus pi by 6. Okay. Now, this is the fundamental component which you have extracted from the Fourier analysis, and finally, if we want to calculate peak value of Vph, I think this is the peak value, this is varying. So, this you cannot include as a magnitude. So, 2 E by pi and cos pi by 6 is root 3 by 2, very good. So, you get this as root 3 E by pi. This is how you calculate the peak value of the phase voltage of 180 degree mode, as you can see over here, root 3 E by pi, that is 120 degree mode phase voltage peak value. Now, for this RMS value, if we want to find out RMS, what you are going to do is root 3 E by pi, which you have already obtained, multiply it by 1 by root 2, you will get the RMS value. So, obviously, you get this as root 3 by 2 into E by pi. As you can see in the tabulated form also, RMS phase voltage for 120 degree mode, it is root 3 by 2 E by pi is the value. Similarly, you can find out line voltage, peak line voltage for 120 degree mode, that is VL 120, you will have to do, and that too also peak value. So, VPH peak into root 3. So, you get this as 3 E by pi. And to find out, to add on to this, what we will do is VL 120, instead of peak we will take RMS value. How you can to calculate RMS, that is VL peak upon root 2, isn't it? RMS is by root 2 and VL peak is 3 E by pi into 1 upon root. As you can see, the same has been tabulated, which I have shown you here with the calculation Fourier analysis. The same has been calculated and tabulated in the form of 120 degree mode and 180 degree mode. Now, in case of 180 degree mode, the fundamental component was extracted as already shown in the previous slides, that is 4 E by pi cos pi by 6 sin omega t plus pi by 6, and in 120 degree mode only E will be replaced by E by 2. So, if you know and if you are clear and if you have understood about 180 degree mode, you will be easily able to analyze 120 degree mode or vice versa. That means, if you have 120 degree mode analysis, you can get the 180 degree mode analysis, or you can other way around also, you can have both the things. So, you have to understand the minute details of one of the modes. If you remember one of the modes, you will automatically remember the other modes, because there are points of similarity, there are points of dissimilarity. The things that you have to keep in mind is, in the tabulated form which I summarized, this is very useful for competitive exams. These formulae are useful for GATE objective questions. These formulae are useful for your end semester examinations. Any kind of theory paper, engineering services, any competitive exam, if you have understood one form of 3 phase voltage bridge inverter, you can have another mode of operation as well. Now, the things that you have to keep in mind is the output voltage of such an inverter, which is operating in either 120 degree or 180 degree, definitely they are fixed. You cannot change the magnitude. Once you have designed such an inverter, you cannot change the magnitude of that output. But in certain industrial applications, we require different speeds, and accordingly equivalent different voltages are required. For example, we have locomotive, we have in locomotive we have AC induction, 3 phase induction motor, and that has to be controlled. The speed of that particular induction motor is to be controlled. Now, in this case, you have to have, according to the desired speed, you have to have equivalent voltage available at the input of the motor, which is obviously the output of DC inverter, and this requires different voltage levels for different speed operation in different industrial applications, commercial applications. So, obviously, what you have to do is you have to have a control at the output of the inverter voltage, which is possible not through these two modes, but definitely it is possible by applying certain modulation techniques, which we call it PWM, or you can say pulse width modulation technique. Now, this technique has got another added advantage, which we will be discussing in some other lecture, and we will see that how PWM technique changes the or controls the output voltage of the inverter, and how it helps in managing or minimizing or mitigating even the harmonics as well. These are the tabulated forms. You remember these, and whatever I have taught you, just go through the lectures once again, and you will find that these lecture in tabulated form, whatever formulae that I have done and what are the points and of similarity and dissimilarity in the previous lecture will definitely help you in solving questions related to gate. Now, these are the you can say straight questions, numerical questions which are available in objective part of the different competitive exams, where you can apply these formulae and get the answers as well. You needn't have to go through all the derivation part of Fourier analysis. Just remember these formulae and you are done through it. Now, to conclude with this lecture, thank you very much for once again for listening to me, and I am here for your lecture too. I was here and I tried to explain the basic part of modes of operation of 3-phase voltage source inverter and its you can say applicative part by extracting the fundamental component of a 180 degree and 120 degree mode, and from that we can calculate how much harmonics are present, I mean which are the harmonics present and how much in quantity they are present. So, the analysis part is also quite good. Now, in further lectures we will see that how the output voltage of inverter is controlled using certain techniques. Thank you once again. Thank you very much.